Hi everyone, welcome to the second tutorial of the Introduction to Machine Learning course. So in this tutorial we shall be taking a tour of the aspects of linear algebra which you would need for the course. We will cover a variety of concepts such as subspaces, basis, span, and decompositions, eigenvalues, eigenvectors over the course of the tutorial. So the first question that one would ask is why we need linear algebra at all and what is linear algebra? So you may have come across this in school or your plus one or plus two level, but just to recap, I mean linear algebra is the branch of mathematics which deals with vectors and vector spaces and the linear mappings between these spaces. So why do we study linear algebra here, especially in the context of machine learning? Is firstly, it gives us a way to manipulate, represent, and operate sets of linear equations. But why do these linear equations come up in machine learning in the first place? So the reason for that is in machine learning we represent our data as an n cross p matrix often, where n is the number of data points and p is the number of features. So it's natural that we have to use notions and formalisms developed in linear algebra, not just the data, even I mean the parameters you use are represented as vectors. So as a result, linear algebra has an important role to play in machine learning. So we can see here a system of linear equations, two equations and two variables, 4x1 minus 5x2 equals minus 13 and minus 2x1 plus 3x2 equals 9. So we can right away see here the advantages of a matrix notation. So if you see below, you can represent the same system of two equations directly as one equation in the form of ax equals b, where a is the set of coefficients and x is the 2 cross 1 matrix, two rows and one column, or you may also call it a two-dimensional vector x1, x2. So we can see that when you multiply the matrix A with x1, x2, the 2 cross 1 matrix, you will get back the same LHS or the set of two LHSs, and B, the matrix B represents the RHS. So you can, it's very easy to verify that if you represent this in matrices, you can get back the original representation, and from that representation you can get this. So to solving this in general without matrices, how you would solve this is you would first solve for one variable and then substitute to get the other. But this using matrices you can even solve this directly. So just multiply both the sides by A inverse. So you would get x as A inverse B. Of course, the nuance you would have to care about is that all matrices don't have an inverse, but in most cases they do. So in that case, you can directly get the solution of x in the form of x equals A inverse B by solving it just through one equation. So as we said earlier, in linear algebra gives you this freedom to manipulate several equations at once in multiple variables. A fundamental definition in linear algebra is that of a vector space. A set of vectors V is said to be a vector space if it is closed under the operations of vector addition and scalar multiplication, and in addition satisfies the axioms we have listed here. By closed we mean that if we take two elements from this set x and y, then x plus y also lies in the set V. In addition to this, if we take a scalar alpha, a real number that is, and multiply a vector from this set y with it, then alpha y also belongs to V. If both these properties are satisfied, then the set of vectors is said to be closed with respect to vector addition and scalar multiplication. Now let's have a look at the axioms. The first one is the commutative law. The commutative law states that if you pick any two elements from the set V, x and y, then x plus y equals y plus x. The associative law says that if you pick any triplet from this set x, y, z, then x plus y added together plus z is equal to x plus y plus z added together. The additive identity law says that there exists an additive identity or a zero, so as to say, in the set, such that if you pick any element from the set and add this zero to it, you get back the same element. The additive inverse law says that there exists for every element, there exists another, for every element x, there exists a corresponding x bar such that x plus x bar equals 0. The fifth law is the distributive law. This law says that if you have a real scalar alpha with which you multiply the sum of two vectors x plus y, then that should be equal to alpha x plus alpha y. The second distributive law says that if you have the sum of two scalars multiplying a vector x from the set, alpha plus beta into x, then that should be equal to alpha times x plus beta times x. The associative law says that if you would first multiply two scalars and then multiply the vector with them, that should be equal to multiplying it first with the second scalar beta and then with alpha. The unitary law says that on multiplication by the scalar real number 1, you get back the same vector. So this is important because you don't want multiplication to cause any unexpected scaling. Like if you multiply by the scalar k, then the vector should be exactly k times. It shouldn't be, say, root k. A second related definition is that of a subspace. A subset W of a vector space V is said to be a subspace if W is a vector space. Now this means that W should be closed under vector addition and scalar multiplication. It should also satisfy the 8 axioms we stated earlier. Now the question that arises is, do we need to verify all these 8 conditions given that we know that W is already a subset of a vector space? No, it's enough to check just for the following 2 conditions. Firstly, that W is non-empty, that in other words it has at least a single element. And secondly, that if I pick any 2 elements x and y from this set, and any real number alpha, then x plus alpha y should belong to W. Now let's have a look at the definition of a norm. So intuitively, a norm is a measure of the length of a vector or its magnitude. It's a function from this vector space, which mostly happens to be R per n, where n is the dimension of a vector, to the space of real numbers R. So for a function to be a norm, it should satisfy the 4 conditions which we have given here. Firstly, it should always be non-negative. Secondly, it should be 0 if and only if the vector is 0. Thirdly, for every vector, if you multiply it by a scalar, its norm should get multiplied by the modulus of the scalar. By modulus here we mean the absolute value. And fourth being that if we take any pair of vectors in our vector space, which is R per n, the norm of the sum of these 2 vectors should be less than the sum of their norms, which this is also known as triangle inequality. So this is in some way related to the fact that the third side of a triangle should always be less than sum of the other 2 sides. Now an example of a norm is the LP norm, where you sum up the absolute values along each dimension raised to p, and then take the 1 by pth root of this. So when p equals 2, you get the L2 norm, which is the magnitude of a vector, as we have learnt in our earlier studies, root of x square plus y square, if you are looking at just the space R square. There are other norms. For instance, there are norms defined for matrices as well. Here we had defined norms for for vectors. So the Frobenius norm is a matrix norm. So what it does is it essentially sums up the squares of all the elements and then takes the root of that. So this also happens to be equal to the trace of A transpose A. Now the trace of a matrix is simply the sum of its diagonal elements. The span of a set of vectors is the set of all vectors which can be composed using these vectors by using the operations of vector addition and scalar multiplication. So the name span comes from the fact that this set of vectors spans a potentially larger set of vectors, which is then called a span. So to define this more formally, it is the set of all vectors V such that V equals sum over I equals 1 to I equals mod x alpha I xi, where alpha I is a real number. Now, a related definition is that of range or column space. So, if we think of a matrix, each of its columns is a vector. So, the set of all columns of a matrix is like a set of vectors. Now, the span of this set of vectors is called the range or column space of that matrix. So if you consider the matrix given here, the the columns of this matrix A are 1, 5, 2 and 0, 4, 4. So what would be the column space of this matrix? It would be the span of the vectors 1, 5, 2 and 0, 4, 4, which is essentially the plane which is spanned by these two vectors. If we have a matrix A of dimensions m cross n, then the null space is the set of n cross 1 vectors which give an m cross 1 zero vector on being multiplied by A. In other words, it's the set of vectors x such that Ax equals 0. Nullity is the rank or dimensionality of the null space. We will revisit the definition of nullity later once we have defined rank more clearly. Another interesting fact about null spaces is that the null space of A, n of A, is of dimension n, while the range of A, or the column space as we defined it earlier, is of dimension m, or m cross 1. This means that vectors in R of A transpose, so note that A transpose is n cross m. So vectors in the range of A transpose will be of dimension n, similar to the vectors in the null space of A. So this means that the vectors in the range of A transpose and null space of A would both be of the dimension n cross 1. Let us consider an example to illustrate the concept of a null space. Consider the matrix A given here. A is a 3 cross 2 matrix. Hence, the null space of A will be made up of vectors of dimension 2 or 2 cross 1. Now we see that on solving, we get u equals 0, v equals 0. This means that the null space only contains the 0 vector, the two-dimensional 0 vector 0, 0. Let's consider another example to illustrate null spaces better. Take the matrix B, which is a 3 cross 3 matrix. The null space would consist of 3 cross 1 vectors. We leave the finding of the null space to the audience as an exercise. However, when on solving, we get the null space to be the set of all vectors of the form x equals c, y equals c, and z equals minus c, where c is any real number and x, y, z refer to the first, second, and third dimensions respectively. Before we dive into defining linear independence, recollect how we defined a linear combination. A set of vectors is linearly independent if no vector in the set can be produced using a linear combination of the other vectors in the set. Now, let's have a look at the related concept of rank. So, the column rank of a M cross N matrix A is the size of the largest linearly independent subset of columns. Note that our columns here are M cross 1 vectors. The row rank is defined in a similar way for rows. Let us walk through some interesting properties of ranks. For any M cross N matrix of real numbers, the column rank is equal to the row rank. We refer to this quantity as the rank of the matrix. Earlier we had looked at a quantity called nullity. Nullity is the rank of the null space of A. Some other interesting properties of ranks are also listed here. For instance, the rank of a matrix is at most the minimum of its two dimensions, the row dimension and the column dimension. Secondly, the rank of a matrix is the same as the rank of its transpose. Thirdly, if you multiply two matrices A and B, the rank of the resultant matrix is at most the minimum of the ranks of A and B. If you add up two matrices, the rank of the resultant matrix is at most the sum of the ranks of A and B. A square matrix U of dimension n cross n is defined to be orthogonal if and only if the following two conditions hold. Firstly, all pairs of distinct columns should be orthogonal. By columns being orthogonal, we mean that the dot product of any pair of distinct column vectors is 0. In other words, Vi transpose Vj equals 0 for all I not equal to j. The second condition is that the dot product of any column with itself, or Vi transpose Vi, equals 1. In other words, all the column vectors should be normalized. An interesting implication of a matrix being orthogonal is that UU transpose and U transpose U both end up being equal to the n cross n identity matrix I. This also means that U transpose equals U inverse, or the transpose of such an orthogonal matrix is also its inverse. An additional interesting property is seen when we multiply a n cross 1 vector x by an n cross n orthogonal matrix U. The Euclidean or L2 norm of such a vector x remains the same on multiplication by U. Intuitively, we can understand this as orthogonal matrices U performing only pure rotation on multiplying the vector x. In other words, they only change the direction of a vector but do not change its magnitude. We often encounter the quadratic form, which is the vector equivalent of a quadratic function. The quadratic form with respect to the matrix A of a vector x, where the matrix A is n cross n and the vector x is n cross 1, is given by the real number x transpose Ax. Based on the quadratic forms of matrices, we can classify them as positive definite, negative definite, positive semi-definite, and negative semi-definite. A matrix A is said to be positive definite if its quadratic form is greater than 0 for any vector x. Similarly, we can define it to be negative definite. A matrix A is positive semi-definite if the quadratic form is greater than equal to 0 for any vector x. Note that equality with 0 also may hold here. One important property of positive and negative definite matrices is that they are always full rank. An implication of this is that A inverse always exists. For a matrix A, which is of dimension m cross n, one can define a special matrix called a gram matrix. The gram matrix is given by A transpose A. The salient property of the gram matrix is that it is always positive semi-definite. Moreover, if the number of rows exceeds the number of columns, in other words, if m is greater than equal to n, this implies that G is positive definite.